Hey folks, lab number 4 is called Combining Forces, and the packet should be right there in the info. You're probably staring at it while you're watching this video. Here's the problem. There's equipment that's here at Finger Lakes Community College that costs a whole lot. So we have to be a little ingenious about being able to do this at home. Let me show you some of the equipment we have here.
The force table that costs $600 if you bought it. So we got to come up with some way of being like this, but at home. You can either hang weights on there with the pulleys, or we would do something like this on a force table, and then you read the forces right on the springs. So you can either use your springs, or you can use your hanging masses, and come up with 3 or 4 different scenarios. So put the sheet of paper in there like that, put a little dot right in the middle, trace this so you know which way, and then write down the forces that the scales read. And you have A, B, and C, but it doesn't matter which way. And then just do that 4 different times.
Hey onliners, this is the lab number 4 force table, and we have to make our own at home. Oh boy, you get points for ingenuity on this one. Here, let me show you what I did. It's really pathetic. Here goes. I did the dreaded potato chip holder clips with the twist ties and the scale, and a shower curtain as the ring, and I got 3 of them going. On this particular table, I had trouble using these guys because of the little fancy lip on this table, but a card table or something might work really well. Then you would just hang the weights over the top with the string. You don't even need the spring scale, because whatever it weighs, you know that 1 kilogram weighs 9.8 newtons on planet Earth, so 100 grams hanging from here would be 1 newton. So you would hang 5 kilograms on that thing, and you got 5 newtons. Okay, so I'm going to do it with the spring scales and show you what I did over here. I didn't want to cut the string. You guys can cut the string because that's what it's for. And there's the spring scale there, there, and there. And I'm pulling, and I'm making readings happen right there, and right there, and right there. You call one of these A, one of these B, one of these C. Doesn't matter which ones you pick. And then you put a piece of paper underneath, and you trace out where those things are all coming from. Probably the center of the circle or the ring would probably work the best. Alright, so look at over here. Look what I did. I just put a piece of paper over here. I'm going to put a dot right in the center of whatever ring, maybe a wedding ring, whatever you want, I got laying around. And then put a dot right in there. I got the intersection of those 2 guys, like the perpendicular bisector. Put a little dot right there. And then a dot over here, which is where these scales are all coming from. Okay? And then I am going to write down which one is A, which one is B, which one's C. Let's pick this one here as A, doesn't matter. And A is equal to, if I get my glasses on, and I read the scale, and it says 5.3 newtons. 5.3 newtons. And scale B, let's call this B. Doesn't matter. Again, you could pick any ones as whatever you want. It's 3.7 newtons. And C is called the equilibrant. That's the fancy word for the force pulling in a way opposite of these 2 resultant. Okay, now C is the equilibrant. The equilibrant is the exact opposite of the resultant of A and B. Remember from chapter 3 that when you add A vectorially to B, you're literally putting the tail of one vector on the head of the other, in your mind at least, and then you get what's called a resultant. And C is stopping anything from moving. It's called equilibrium, no net force. So C actually cancels it all out. So that's, let's see, 2.7. Now once you get that, and you wrote that all down, then you can take this, this paper up, and then change the configuration over here. Move this somewhere else so that there is a different reading on the scale. Kind of tweak these guys a little bit, and then do it again. do the whole thing over again. Okay? Alright, now let me show you how to get this done. You need a straight edge and a protractor. Okay, stop that tape for a second. Alright, so now we're going to just connect the middle line to there. There's the line of sight of vector A. We can even put an arrowhead on the other. And here's vector B right over here. And vector C that goes right over here. Of course, I wrote it right down in the middle of the thing. So that's right here. Okay? And now we draw these to scale. So either on a piece of graph paper or even on this thing. If the paper is big enough, you can actually do it on this. Draw A to scale. 5.3 newtons, maybe that'll be 5.3 centimeters or 5.3 inches if you're really crazy and you like inches. Okay? So make this to the right length. Then get a protractor and measure this angle. We call it measure angle 1. And then you have to take B and move B and put it on the tail. Put the tail of B on the head of A. Or take A and put it on the head of B. Either way, you're going to put one on the head of the other. Draw a line from the origin to the last head of the last vector you drew. That's the resultant, and I don't know why, but this write-up calls that letter D. It should be called letter R for resultant. Okay? D, when you put the tail of A on the head of B, you might get something like, this might be this big, and A might be this big, and you put the tail on the head of B, then you end up with a line drawn that's A redrawn so that it's on the head of B. And then D is from the origin to the last head of the last vector drawn. Guess what the size of B should be? D. What should the size of D be with respect to the equilibrium? Think about that. What should the angle between C and D be? Think about that because I'm actually doing the lab for you. Alright, do that 4 times and somehow prove it to me and you win valuable prizes. Alright, here's how to get a 20 out of 20 on lab number 3, the force tables. So, you need the 4 data graphs somehow all written up in such a way where I know you did it. So I'm going to see the tables on the thing you hand in, but also hopefully maybe you could scan it in, or maybe you can show me a picture from your phone. Somehow, see if you can show me that that you did the actual work. I trust you, but try it anyway. See what you can do. Fill out all the answers to all the questions in the lab packet, and then just write me a paragraph. They told me that you understand the gist of the whole thing. Mini lab, real quick, real easy. I'm just looking for you knowing how to put the tail of one vector on the head of the other vector and drawing a line to get the resultant vector and the equilibrium being equal and opposite. Hopefully, I just gave you the answer to that question. Also, do one of them at least with components. I need for you to know how to do it with pure math from chapter 3. Okay? So, that's worth 20 out of 20. Let me know how you do.